The previous section we understood or learned the concept of naming chemical compounds. Whenever we learned writing down chemical formulas, one thing came into mind, and that was the ratio. Ratio was very important in finding out the true formula of a compound. So, for example, when we write sodium chloride, then why is the ratio 1:1 for sodium chloride? And however, if you write sodium carbonate, then if you recall, we had to put a 2 in front of a subscript over here. So why is the ratio of sodium, carbon, and oxygen in this format? We've already gone through the depth study on that, so I'm not going to go into it. But keeping the concept of ratio in mind, this new chapter will talk about how we account for the number of atoms when an element or a compound undergoes any kind of reaction. So when elements or compounds undergo a reaction, there are two scenarios. One is a reaction in which there is a physical change in the appearance of a compound. For example, melting of ice and boiling water. In both of these instances, the formula of the molecule is still water. It will be ice as solid, liquid as water, and gas as steam. Another example is if you take a log of wood and divide it into two small portions. We still have the original, the material, which is the wood. If you take a piece of paper and tear it into smaller and smaller pieces, you still have the consistency of the paper. So in all of these examples, the composition has not change. So that's important. Any reaction in which the substance does not appear to change in its composition is termed as a physical reaction. State in which there can be no change, but material can be broken down from larger to smaller pieces is still a physical reaction. On the other hand, a reaction in which there is a chemical appearance that has changed. For example, if I added a drop of antacid to this glass of water, and which the formula of antacid is sodium bicarbonate, you see the fuzz over here, which is the appearance of the carbon dioxide. You also have sodium carbonate all coming out. So the substance is no more there as sodium bicarbonate. Another example is over here, in which you see the rust is being added to the iron. And the reason for that is that iron reacts with oxygen from the atmosphere to give you this new compound, which is the rust, iron 3 oxide, which layers on all these nails that you see. So in all of these, in both of these reactions, old bonds are broken and new bonds are formed. The new bond results in the formation of a new compound. Thus, these reactions are called as chemical reactions. Based on the chemical reaction, we have a very important law in chemistry, which is called as the law of conservation of mass. Law of conservation of mass holds as accountable for chemistry as the evolution law for biology, or the Newton's law of gravity for physics. Law of conservation of mass states that matter cannot be created nor destroyed. So in other words, I can't just take A and B reactants and form AB unless I have the starting substance of B or A. In other words, we can't just magically appear substances. Another important factor of this law is that the total mass is always conserved. So for example, if I have a reaction in which I produce 2 ABs, I cannot just produce that by one of each. I would have to have 2 of the A's and 2 of the B starting substance to form 2 ABs. And thirdly, it is that the mass of all of the products which are formed over here on the right hand side are always going to be equal to the reactants. So for example, let me give you a simple example of 10 bicycle frames. If we have 10 frames and we need 20 wheels to construct a bicycle. Now, a bicycle which holds 10 frames and 20 wheels, you can see we will come up with 10 bicycles. So this is an accountability of how many starting substances we have. So, for example, if we have 8 frames and we still want to come up with 10 bicycles, there's a problem over here because we do not have enough starting material. So this is what the law is talking about, that matter cannot be created nor destroyed. And now if I check the mass of these 10 bicycles, that should total the mass of the 20 wheels plus the 10 frames. So keeping this simple example, in mind, we will now go and look at the next the laws. Okay, here is an example of a chemical equation. A chemical equation is firstly a simple one-statement reaction. It's a reaction in which you're using one statement. The statement has parts. On the left-hand side are your reactants, and on the right-hand side are the products. And they are separated by this arrow, which is showing the arrow is pointing towards the product, which means all the reactants are going to convert into products. A lot of times you will find information that's written below or above the arrow, and any information over here is going to be either, for example, a temperature or a catalyst, or certain ions, or any other supplementary information that might be needed to form this product. Other than that, you also find symbols. Symbols are those of the starting substances and symbols of the formulas. The symbols will give you, as I said, reactants and products both. The reaction conditions are exactly what I said over here, information that's present around the arrow. And lastly, you will always have the number of reactant must be equal to the product atoms. For example, if I break this down, I see that there is one carbon atom and there are 2 oxygen atoms. Does that make sense to you from this formula? And if I look at this atom over here, I have 1 carbon and I have 2 oxygen atoms. So this states that the number of carbon on both sides are equal and the number of oxygen on both sides are equal. This is accountability. Now let's look at this concept in a process and learn about how to balance chemical equations. Again, chemical equation is going to be your one-line statement that is shown in this part. This is a chemical equation. Now, in this chemical equation, if I was to count for the number of aluminum on my reactant side, I see there's only 1 atom here and there are 2 atoms over here. So where did this extra aluminum atom come from? Let's also observe the sulfur over here. The sulfur is represented as 1, so that's 1 atom of sulfur, and in this compound you can see that there are 3 atoms of sulfur. So you cannot magically appear atoms of any element. Now, the only explanation to this equation is that the equation is not balanced, and the equation has to be balanced by using these numbers, which are called as coefficient. Coefficients are a whole number that is placed before the element's name or the compound's name. And the easiest way to find what kind of coefficient or what number is to use is by looking at the subscript of the formulas. The subscript will give you a hint. For example, there is 2 over here, so a coefficient of 2 is placed in front of aluminum. Here is a 3 on the sulfur, so a 3 is placed in front of the sulfur. And these writing this formula with ALS is giving me Al2S3. So keeping the 2 in front of aluminum and writing 3 in front of the sulfur, I am now reading the formula as 2 atoms of aluminums react with 3 atoms of sulfur to give a formula of a compound which is aluminum sulfide. Now I cannot just use aluminum and sulfur and come up with a formula of ALS, because you did in the previous chapter learned about how formulas are constructed, and the formulas of every compound is unique. For example, let's refresh back. You have 3 ionic chart for aluminum and 2 for sulfur. So if I do the cross my heart thing, I know that the formula of aluminum sulfide is going to be exactly the way it is. So keeping this in mind, you learn how to balance reactions. Here is another example in which a reaction is shown to you, which is iron oxide. And you can see this is iron 4 oxide reacting with hydrogen, forming excuse me, the element iron and water. Now, the information that's written over here, which is the solid, gas, and liquid, is sort of irrelevant, and you can ignore that. What you need to focus is the number of let me just make a straight line over here. If I write down my iron on this side, my oxygen over here, and hydrogen, and let's just count each, and we see that there are 3 of this. There are 4 oxygens, and there are only 2 atoms of hydrogen. On the other hand, we see over here we have 1 atom of iron, we have 2 atoms of oxygen, and we have 2 atoms of hydrogen. Actually, I'm sorry, this should be 1. And there are 2 atoms of hydrogen. So you can see that each of the element is not balanced. It is not accounted for. Whenever you have 3 different elements that are all not balanced, you should always pick up 1 element at a time. So for example, let's just always begin with the metals because they're easiest to balance. And then we'll pick up 1 element and the other element. So 1 at a time. So since there is a 3 over here, this 3 is a hint to place a 3 in front of the iron. Now once I place that, I go back and review. It seems like my iron are now balanced, but I still have oxygen and hydrogen. So since I have 4 of oxygen on this side and I have only 1 over here, so the easiest way is to put a 4 in front of the water. Now note, I cannot just break in and write down H2 and then a 4 and then oxygen. Why? Because there are some strict rules we learned about writing formulas, and the formula of a compound is clearly the way it is shown over here. You cannot just break into a formula and put in a coefficient as wherever you want. So by writing the 4 over here, this 4 is now taken like this, just like you would do as an algebra problem, which if I was to break this shows that there are now 8 hydrogen and there are 4 oxygen. So my oxygen is balanced, definitely, but what happened to my hydrogen? Now I have 8 of these hydrogens. Because I have 8 of the hydrogens over here and there are only 2 on the reactant side, I'm using my factors and writing a 4 in front of the hydrogen, which accounts for 8. Now once I've done this in 3 steps, a reaction many times needs to be balanced in 2 or 3 steps. Once you have balanced a reaction, you really don't know if it's complete or not. The best thing to do at the end is to always check yourself. So once you have done the reaction, go back and review and see if the reaction is all accounted for. And if I check myself for this last reaction and account for each iron and oxygen, I see now that I have 3 on this side, I have 4 oxygen on this side, and I have 8 hydrogens. I go on the product side, I find that there are 3 atoms of iron, I find that there are 4 of oxygen, and I find that there are 8 of the hydrogens. So this concludes that my formula is now completely balanced. Here is another example using an equation in which I have shown you NH3, which is ammonia reacting with oxygen, forming nitrous oxide and water. Again, make a straight line like this and write down each of the elements. You have 1. If I write down hydrogen, I have 3. And if I write down oxygen, I have 2. On my other side, I have 1 nitrogen. If I write down the oxygen, I find that there is 1 here and there is 1 here. So there are altogether 2 atoms of oxygen, and there are 2 atoms of hydrogen. Now, keep in mind, whenever you have an atom that is present on 2 of the products or 2 of the reactants, you always add them up. The reason, if the purpose or the reason for that is that atoms always collide and make changes, forming new bonds. So as long as the accountability of an atom is there, then it is a part of that reaction. Now, keeping that in mind, we can see the nitrogens are balanced, but our hydrogen is not, and our oxygen is balanced. Now, even though it seems like we shouldn't really need to worry about the nitrogen, but I will have to balance my hydrogen. And since there are 3 on this side and 2 on the other, now I'm going to use a factor concept to come up with the whole number. So I put a 4 in front of the ammonia, which is 4 times 3 is 12, and that gives me to place a 6 in front of the hydrogen, which gives me 12. And now I have 6 oxygens, and I have let's go back before we do the oxygen. Let's go back and check on the nitrogens. We see there are 4 nitrogens here, so we will have to place a 4 in front of the NO. When we placed a 4 in front of the nitrogen, we also now have 4 oxygen and 6 over here, so that's 10 oxygen. So that's why we came back on the reactant side and put a coefficient of 5. Now this is one of the difficult ones that you might experience to do. You might be wondering, why didn't I start working with a 2? I'll show you what happens if I start working with a 2 to balance this. If I was to place a 2 here, then 2 times 3 is 6. Okay, let's go ahead and place a 3 here. 3 times 2 is 6. But then I have 2 in front of the nitrogen, so I will place a 2 here. Now if I have 2 here and 3 here, this gives me oxygen that are 5, and it's kind of hard to come to balance that number. So that's why I could not work this problem with the lower coefficient, and I had to choose a 4. This will happen many times when you start doing a problem. You will find that even if you use the smallest ratio, sometimes you will get stuck on that ratio and you pick up the next higher series of the odd or the even number. Now, here is another example in which we are balancing, but we're using polyatomic in the equation. Now, if you have polyatomic, then the best way to do that is to keep the polyatomics as one unit. So do not break phosphate and oxygen to balance them out. Consider them as a unit. Now, when you consider them as a unit, it makes it a lot easier to balance them. So I have a 2 here. I place a 2 in front of the sodium phosphate, and then I go back and review all my numbers. Now I have 2 times 3, which is 6 sodium. Initially, I had only 1 sodium. So while balancing one element, I find that I've unbalanced the other atom. So I place a 6 in front of the sodium. When I place a 6 in front of the sodium, now I have 6 chlorine atoms. So I go back on the previous side, which is the reactant, and put down a coefficient of 3, because 3 times 2 is 6. When I do that, and let's go back and review our equation. We have 3 magnesium. We have 3 magnesium. 3 times 2, 6 chlorines. We have 6 chlorines. 2 times 3, 6 sodiums, 6 sodiums. And we have phosphate, which is 2, and then phosphate, which is 2. So now here's an example in which balancing one element will always, most of the time, unbalance another element or a compound. So again, before we go on to the next section, let's review the parts of balancing. Always first account for the total number of atoms. Find out which atoms need to be balanced. Secondly, work with small whole numbers, or use fractions if you have to get the concept about which whole numbers to use. Balancing one element unbalances another element or a compound or polyatomics. So go back and check on that. And lots of practice are needed for balancing. I have given in your lecture packet at the end, we have Appendix 3, and Appendix 3 gives you a lot. I think it's 3 or 4. I'm not too sure. Just check with this. And this appendix at the end gives you lots of reactions to practice on, and we will probably be doing some in the class as well. Our next section is about mole. Mole is a collection term that is used in chemical terms. Just like if I use the term dozen, whether I say dozen donuts, a dozen roses, a dozen eggs, the number 12 comes into your mind. If we see a ream of paper, we mean that there are 500 sheets. So if you say 2 reams of paper, we know there are 1,000 sheets. If we say a case of sodas, that is 24. So each of these terms signifies a certain number of quantities. Similarly, there is a quantity which is called as the mole. Mole is the origin of mole is a Greek word which is heap, or a lot of amount of a substance. A mole is a very large amount. The quantitative number is 6.02 10 to the power 23. Now you can imagine, if I was to take away this decimal, then I would have to place at least 21 zeros over here to come up with this large number. This large number is also called as the Avogadro's number. This is the number or the quantity of any particle, whether it's a particle or whether it's a number of molecules, or whether we're counting formula units. In other words, whenever we are counting something, and chemistry will usually be counting ions, we will be counting atoms, and we will be counting formulas, or as you can say, compounds. So any of these will be used to quantify by the term mole. And if you say 1 mole of sodium atoms, then it would be 6.02 10 to the power 23. If I say a mole of hydrogen atom, then it's again that same large number. If I say a mole of water, then that means that it's a molecule, and there will be as many number of molecules. If I say a formula unit of sodium chloride, then that is again that large number. So again, a mole can be expressed as a quantity, as shown in this slide. The quantity has a very large value. The mole, using the statement previously, which was an equality, in which we said that a mole equals 6.02 10 to the power 23. We can use this equality to then determine either particles or moles in any kind of statements or mathematical problems. So for example, how many copper atoms are in 0.5 moles copper. Now again, this is the same thing we learned in chapter 1. You begin with what is given to you, which is 0.5 moles copper, and now you see that the mole is here, so my unit of mole should be on the bottom. I should put the quantity on the top. Once I cancel these, my value is 3.0 10 to the power 23. I hope everybody remembers to put 6.02 first on your calculator. Then the next key you should press in is your EE or your EXP key, and then you put in the number 23. That's all you have to put in. The EXP or the EE key gives the factor of 10 to the power of n. So when you're saying n is 23, you're already putting that in. So I repeat, do not put in the multiplication sign that's shown over here on your calculators. You're just going to put in 6.02 EE or the EXP. Lately, I've actually seen some calculators that even have this little symbol or the key on it. So find your key for the EE. If not, come see me during class and I'll show you. Here is another example of a problem in which we're using the same equality to find out how many moles of carbon dioxide are present in that many number of molecules. So here we are beginning with the particles or molecules. So now my equation is going to have molecules or particles on the bottom. Again, notice this is given on the bottom. I cancel these units, and once I divide 2.5 by 6.02, I get the answer in moles. Now both of these problems, the one over here and the one over here, is using exactly the same dimensional analysis in which we use a conversion factor of one or the other depending on what our question is asking for. Another concept that we want to go in this chapter is the molar mass. Molar mass is, as the name tells you, it's the mass or the weight of a mole of a compound. So for example, if I say go get me a dozen eggs or a dozen donuts or a dozen cantaloupes, you can imagine that they're all going to be 12, but the mass of each is going to be different. So similarly, if we say 1 mole of hydrogen, or we say 1 mole of sodium, or we say 1 mole of copper, or 1 mole of carbon, a mole, if you were to count the particles of each, will be that Avogadro's number. However, the mass is going to be the atomic weight expressed in grams. So the atomic weights for each of these are written on the periodic table. So when you look at the element, notice that you have atomic weight on the bottom, and that is going to be expressed in grams. Similarly, sulfur, we have the atomic weight as 32, expressed in gram. Silver, atomic weight of 108, expressed in gram. So a mole of any element is its atomic mass expressed in grams. However, if we were to take a mole of a formula, for example, calcium chloride, then we have to account for the number of particles there are. Calcium, there's 1 particle. The atomic weight is 40, so we go ahead and write that. Chlorine, as you can see from the formula, there are 2 of these atoms, so each is 35, total 71, and then you add these 2 up and you get the total of 111. So for example, if I was to take atomic mass of or the total molar mass of water, then hydrogen is 1 times 2, because there are 2 atoms of hydrogen, plus 16 grams of oxygen, which totals 18. Here, let's do another example with carbon dioxide. Carbon has 12 as the molecular weight, oxygen 16 times 2, so that would be now 12 plus 32, which totals 44. So pretty much For each one, you are accounting for the atomic masses of each and adding them up. Let's do sodium hydroxide. Sodium is 23 plus oxygen, which is 16, plus hydrogen, which is 1. So the total will be now, let's see, 40. 40 grams would be the total for sodium hydroxide. So atomic weights are added up together in a compound. Here is an example with potassium phosphate. You can see that there are 3 atoms of potassium. So 3 multiplied by 39, we have 1 phosphorus, and we have 16 oxygen, which adds up to 64. So now when you're adding all these up, the total is the molecular mass of potassium phosphate. In this last section, we will quickly go over the theories of reactions. One of the theories of explaining how reaction takes place is that molecules collide when they have sufficient energy and they break their bonds within the reactants. And later on, new bonds are formed between the reactants and a new compound or a product is formed. So as an example, you have 2 reacting substances colliding, and this collision requires tremendous amount of energy or less amount of energy, and that depends on each reaction, and you get 2 products. Now sometimes you have reactants reacting and the energy is released on the product side. So there are 2 kinds of reaction, and we will review both of them. Now the energy that is needed to activate a reaction is called as activation energy. So for example, on this example of the nitrogen and oxygen, you can see that the reactants are at a very low energy, and the collision requires a very high energy. This amount of energy must be added to this system for the reaction to go on. A reaction in which energy is actually added, I'm going to go ahead to my next slide, as a matter of fact, is called as endothermic, because you're taking in energy, and the energy of the product actually, I'm going to go back now. This was the right one. We were doing this. So if I go back on this reaction, I can see that energy will be added into this reaction. And when the reactants are released, the products will be formed here, and the excess energy will be released. And because the energy is now released, this is called as an exothermic reaction. The other kind of reaction in which the energy is absorbed is called as the endothermic reaction. In endothermic reaction, the products are actually at the higher energy state than the reactant. So energy has to be added to the reactant to form the product. Now, one way of overcoming the barrier of a very high difference of activation energy is by the use of catalyst. A catalyst is a substance or a chemical or it could be of external factor. For example, heat can also be a catalyst. It will lower the rate of activation, and it never gets used up during a reaction, and it always will be recycled. We use the term enzyme only in biology when we're talking about cells. Cells are organic. Enzymes are organic catalyst. When we take catalyst, it could be sulfuric oxide, it could be heat, it could be temperature, even pH. So these are all catalysts. These are all external or factors that will lower the activation energy and increase the speed of a reaction. Now we will go into organic catalysts later on in the last section of the book, in which we'll talk about proteins and enzymes. So this was the last slide. Make sure you know the terminology of catalyst. This chapter had quite a few different terms. We began with balancing, we went over moles, and we concluded with molar mass and the catalyst.